Look in here, we're going to talk about effusion and diffusion. Effusion is the process of a gas escaping or exiting a container. Yeah, sorry, it may be messy back here. Yeah. I put the broken chair back there. Again, I always try to remember that because it starts with the E, so it's the one that talks about exiting or escaping and how our gas molecules do that, usually how fast they do that. A good example of this, like if we were gas molecules, okay, so you have to pretend that you're a gas molecule. This would be you escaping out of my classroom to go home, okay? Example, sorry. My little bullet, sorry, I've developed that back in high school for my example. So diffusion, what prefix do we see in diffusion? Di, what's that mean? Two. So this is the process of gases, plural, mixing. So for example, you meeting up and mixing with other students in the hallway. So the process of you going out would be effusion. Once you're out, you're going to mix with all the other students. That would be diffusion. And again, these two processes happen because effusion occurs because we want to equalize pressures. We saw that liquid coming up into the glass yesterday because it wanted to equalize the pressures, and the only way to do that was to change the volume of our gas. Okay, so effusion happens because we want to equalize those pressures. Diffusion happens because our gases want to spread out among the whole container. Okay. Now, how could I increase the speed of my molecules? What could I do? How could I make them go faster? Okay, if I increase the pressure, that could also increase our temperature, okay? And so ultimately, whether we increase pressure or increase volume or physically heat it up, we want to increase that temperature. So if I increase temperature, I'm going to increase our kinetic energy. That's the energy of motion, which means that I automatically increase the speed or velocity. Again, Ruth, you are exactly right, though. If we mess with the pressure, if we increase that pressure, Gay-Lussac's law says that we're going to increase the temperature as well. If we increase the volume, we're going to increase the temperature as well, which would increase our speed. Okay. Now, according to our kinetic molecular theory, again, KMT, moving molecule theory, as temperature increases, we know that kinetic energy is going to also increase. This is the most important thing for us to look at in terms of speeds. We're always going to look at temperatures first, and then we'll look at something else if we have to break a tie. So I guess my question is, which one of these gases is going to be moving the slowest? The one at 14 degrees Celsius, which is gas F. Yes.
On the diffusion, is that basically like, it's not bonding, but it's
It's just mixing. So,
yeah, it's still it's the same as it was before.
yeah, it's not chemically mixing, and we're going to see something mixed today and it actually goes through a chemical change when it mixes. Most gases, when they mix, they don't actually chemically react because they're moving so fast that they can't necessarily combine. However, there are a few that will react.
And they're like explode, right?
Not necessarily explode. The one we're going to see today, we're going to see a simulation of it. It doesn't explode. Which gas is going to be faster than gas F? C. And then E. B. Again, we're going with low temperature to high temperature. Alright, so we're going to watch a video, which I'm going to post along with this set of notes for those of you watching, okay? So when I go to the video, go to the video. And what we're going to do is we're going to look at two gases. What we're going to end up simulating is that we're going to have two cotton balls soaked in two different chemicals. One's going to be in hydrochloric acid and one's going to be in ammonia. And like all liquids, they're going to try to evaporate. Even water will evaporate at room temperature. And when they evaporate, that means they don't go away, they just turn into a gas. And what do we know about gases and their containers? They like to move around that are constant in random motion, and they're going to try to fill up their container. So whatever gas I have over here is going to try to fill up the whole container. Whatever gas I have on the right side, it's going to try to fill up the whole container. So when we have ammonia, which is NH3 gas, and hydrogen chloride gas, which is technically hydrochloric acid, that's been vaporized, it is actually going to not just mix, they're going to react chemically. This is a base, it has a basic pH, and hydrochloric acid is definitely an acid, and acids and bases react together. And these are going to form a solid. So we're going to have two gases that come together and form a solid. Now what do we call it when we form a solid? A precipitate. And normally we think of like liquid solutions. Well, a solution is just a homogeneous mixture. Well, here we have homogeneous mixtures of gases and air, okay? And so we're still going to see that solid form. It really does form a cloudy film on the outside. Hydrochloric acid. Okay. Well, remember, you can make anything a gas. And we said that we were going to dip our cotton balls in both of them and they're going to evaporate, which means that they're going to naturally turn into a gas.
Well, what if you found a substance?
Everything can at some point in some conditions. Like the table you're sitting at can technically turn into a gas under the right conditions. Yeah, with a high enough temperature or a low enough pressure, yeah. You can get water to boil at room temperature if you have a high enough pressure. Or a low enough pressure. Sorry. Yeah, it is weird, but it happens. Okay, and so like don't think it. Yeah, lower pressure is going to be a lower boiling point. Because those molecules are freer to move because they're not as compressed, which means that they like to turn into a gas because things go to disorder, more entropy. Okay, so we're going to watch the video. We're going to try to figure out which gas is at which end. Okay, and so we need to make sure that we pay attention to not only what's going on, but like speeds of the molecules that we see, as well as things. You're going to notice our two cotton balls on the end. One of them's soaked in hydrochloric acid, one of them's soaked in ammonia, and they are naturally going to evaporate. And we're going to see that those molecules, which we can't necessarily see the molecules, but we have our animation there that's telling us our molecules, and showing them are moving. Now what do you notice faster than the other. We've got different colors and different molecules. Which one would you say is the faster one? The one on the left or the one on the right? The one on the left. Again, we can see it moving faster. Also, did they meet in the middle? No, they met closer to the slow side, right? Okay. And so we're going to take a look here, and we're going to mark this on our tube. Okay? So we're just going to put a line where we're seeing that solid form. Again, I don't want to put it in the middle because they didn't meet in the middle. I do want to put it closer to side B. Again, the farther the gas moves, the faster it's going. So we know that this side is our fast side, this side is our slow side. Now, which one do you think, which gas, ammonia or hydrochloric acid, is the fast one? Why do you say ammonia, James?
Because it's fully, like, it's just,
How could you tell that it was on that end? Okay, so we could tell from the formula. Let's go back to what if we didn't have the shape in the formula?
one is smaller.
How is it smaller?
Well, because, I forget what it's called, but you know, the radius or whatever, you know what I'm talking about.
Okay, so the radius are smaller. So for NH3, we know that hydrogen has one shell, right? And nitrogen has 2 shells for a total of 3 shells, right? HCl, the H has 1 shell, but the Cl has how many shells? What period is it in? Yep. Chlorine's in period 3, and so it's going to be larger. Okay? Now, there's another way that we can talk about size, not just physical size of it or volume. What about mass? If you could be teeny tiny, right, but have a huge mass, are you going to run as fast? No. And so what we're really going to take a look at is molar mass. Now the molar mass of ammonia is 17.04 grams per mole. And the molar mass of HCl is 36.46 grams per mole. Hydrochloric acid is a little bit over twice as big. Is it going to move as fast? No. And so we know that the higher the molar mass, as molar mass goes up, what happens to our speed? It slows down. And so on here, which gas would be our fast one? Yep, our NH3, so that's on our fast end. And which one is on our slow end? HCl. And then right here in the middle is where we made that solid, the NH4Cl. So again, substance A here would be NH3. Substance B here would be HCl. Now this goes back to Graham's law of effusion. Okay? I like to call that my s'more law, because you know I love s'mores. And s'mores are made out of graham crackers, right? And y'all, the more s'mores you eat, the slower you're moving, right? And the more graham crackers, right? So think about it. If you eat 20 s'mores, you're not going to be moving very fast, are you? Nope. So the more s'mores, the more you weigh, and the slower you're going to move. So Graham's law of effusion. Let's talk about that up here. According to Graham's law of effusion, if gases are at the same temperature, again, they have to be at the same temperature first. they have the same kinetic energy but could have different speeds. As the molar mass increases, the speed decreases. And so now it wants us to rank our speeds of all of these gases that are at 25 degrees Celsius. So if they're at the same temperature, I'm going to need to know their molar masses. I'm going to help you out. 117.04, 16.05, 28.01, 2.02, 44.02, and 44.01. So which one should be the slowest? Which is dinitrogen monoxide. What has the largest mass? Again, the heavier it is, the slower it's going to move. Again, 8 more s'mores.
Then
Carbon dioxide. Carbon monoxide. Ammonia should be next, which would be nitrogen trihydride. No, ammonia.
what is and it's carbon?
Because it's 17. And then CH4. Which is called methane. And then hydrogen. Again, you could call it carbon tetrahydride. You could call it that. We typically call that methane. Okay? And again, so we're going to go from high molar mass to low molar mass. Does that make sense to you that if it has more mass, it should move slower? Okay. Well, let us go back and make sure we write that in on our gas law page. And so we have Graham's law of effusion. If molar mass goes up and speed goes down, what type of relationship is this? It's indirect or an inverse relationship.
You said one go up and one go down.
Mhm. If they do opposite, and so here I'm going to put molar mass on my independent axis and my speed on my dependent axis. And what should my graph look like? Should it be positive or negative? Negative, because it's inverse.
You're starting from up.
And it should curve. Now, well, it should be negative going down, and then it's going to curve, because it's not actually linear. It's an inverse relationship. For our formula, if it's an inverse, our variables should be side by side if they're on the same side of our equal sign. If they're on opposite sides, they should be diagonal from one another. And on this Graham's law, we actually put the speeds on one side. Okay. Oh, okay. And so we're going to see our molar masses underneath the square root. Now don't worry, we don't have to solve for this equation, okay? We do need to recognize it, but we don't need to solve for it. And here the variables are not on the same side, are they? So that means that they're going to be diagonal from one another because it's an inverse relationship.
So, quick question. What would happen if we were
You would just multiply both sides by speed 2. Yep, speed 1 over speed 2 is equal to the square root of molar mass 2 over molar mass 1. In fact, we use this a lot to try to figure out what gas we actually have.
So would you, if you were doing molar mass 1, would you have to use square root of everything else?
Nope, you would square both sides. Yeah, you would have to square both sides. Mhm. Yep.
And with the molar mass, so we square
Because if you square both sides of this, the square root goes away. Okay.
Oh, and then you just multiply.
Yep. No, it wouldn't matter if you put 2 on top and 1 on the bottom. Okay? They do have to be diagonal from each other though. Okay? Now, we have a law down below called Dalton's Law of Partial Pressure, and this is what we're going to end up with today. And Dalton's Law of Partial Pressure tells us that the total pressure, remember that pressure is related to the number of collisions. So the total number of collisions we see should be equal to the collisions that gas A has, plus the collisions of gas B, plus the collisions of gas C, plus the collisions of whatever other gases we have in our container. Okay? Yeah. It is. You can do 1, 2, 3s, you can do A's, B's, and C's. The number of collisions is related to the pressure that we see. Okay? Yep. Again, the pressure isn't exactly the number of collisions we see. They're not equal, but they're definitely related. They're directly related. Okay? So Dalton's Law of Partial Pressure, we're going to actually do this example, E11 here, real quick. And yes, we actually can get it done before Hubbard comes on. I know! It says we have a sealed eudiometer. A eudiometer is a gas collecting tube. Hey, we've got a diagram of a gas collecting tube up here. Okay? Right there. And it's talking about our activity, so what we saw up here, and it tells us that the total pressure is 0.987 atmospheres. Now I know that this is a pressure because it says atmospheres, and it tells me that. And it's the total, so I'm going to label that P total. So we can go ahead and start making our list. 0.987 ATM is equal to our P total. I see that the pressure of the hydrogen chloride gas or hydrochloric acid, P, and here I'm going to just label that of HCl. So I'm going to put a little teeny tiny HCl down there so I know exactly what that's the pressure of. That's equal to 0.281 atmospheres. And then it asks for the partial pressure of ammonia. So I'm looking for the pressure of NH3. Y'all, how would you find that? If the whole thing's 0.987, yeah, we're going to end up subtracting. Now, to keep things consistent, we're going to go ahead and write our formula. P total is equal to the pressure of hydrochloric acid plus the pressure of NH3. Again, I'm doing it that way because are we always going to subtract? No, I could be looking for the total pressure. But in this case, I'm looking for that pressure of ammonia. And so I need to make sure it's in the numerator. Is it?
No.
Yeah, it's on top. It's not underneath a fraction. And so now I need to keep it right where it is. And what am I doing to the pressure of hydrochloric acid on the right side? Adding. So I'm going to have to subtract on the other side. And so that's going to be P total minus P of HCl equals my P of NH3. Well, I'm looking for P of NH3. So algebraically, how would I get this pressure by itself? Yeah, I got to move the HCl over to the other side, and it's being added here, so I do the opposite operator on the other side. Okay? Also, I've got the total, and I have one of the parts. I need to know the other part. Yep, you should get 0.706. So here we have 0.987 atmospheres minus 0.281 atmospheres equals the pressure of my ammonia. And when we look at subtraction, we look at number of decimal places. This one goes out 3, that one goes out 3. And so when we subtract, we need to make sure we go out 3. And there is my pressure.
But you didn't even, like, we didn't even really need these other parts. I mean, yeah, we did, but I mean, we didn't really have to